In mathematics, a semigroup is an algebraic structure consisting of a set together with an associative binary operation. The binary operation of a semigroup is most often denoted multiplicatively. XY, or simply XY, denotes the result of applying the semigroup operation to the ordered pair. Associativity is formally expressed as that Z equals X for all X, Y and Z in the semigroup. The name semigroup originates in the fact that a semigroup generalizes a group by preserving only associativity and closure under the binary operation from the axioms defining a group. From the opposite point of view, a semigroup is an associative magma. As in the case of groups or magmas, the semigroup operation need not be commutative. So XY is not necessarily equal to YX. A typical example of associative but non-commutative operation is matrix multiplication. If the semigroup operation is commutative, then the semigroup is called a commutative semigroup, or it may be called an abelian semigroup. A monoid is an algebraic structure intermediate between groups and semigroups, and is a semigroup having an identity element, thus obeying all but one of the axioms of a group. Existence of inverses is not required of a monoid. A natural example is strings with concatenation as the binary operation, and the empty string as the identity element. Restricting to non-empty strings gives an example of a semigroup that is not a monoid. Positive integers with addition form a commutative semigroup that is not a monoid, whereas the non-negative integers do form a monoid. A semigroup without an identity element can be easily turned into a monoid by just adding an identity element. Consequently, monoids are studied in the theory of semigroups rather than in group theory. Semigroups should not be confused with quasi-groups, which are a generalization of groups in a different direction. The operation in a quasi-group need not be associative, but quasi-groups preserve from groups a notion of division. Division in semigroups is not possible in general. The formal study of semigroups began in the early 20th century. Early results include a Cayley theorem for semigroups realizing any semigroup as transformation semigroup, in which arbitrary functions replace the role of bijections from group theory. Other fundamental techniques of studying semigroups like Green's relations do not imitate anything in group theory, though. A deep result in the classification of finite semigroups is Krohn-Rhodes theory. The theory of finite semigroups has been of particular importance in theoretical computer science since the 1950s because of the natural link between finite semigroups and finite automata via the syntactic monoid. In probability theory, semigroups are associated with Markov processes. In other areas of applied mathematics, semigroups are fundamental models for linear time invariant systems. In partial differential equations, a semigroup is associated to any equation whose spatial evolution is independent of time. There are numerous special classes of semigroups, semigroups with additional properties, which appear in particular applications. Some of these classes are even closer to groups by exhibiting some additional but not all properties of a group. Of these we mention regular semigroups, orthodox semigroups, semigroups with involution, inverse semigroups and cancellative semigroups. There are also interesting classes of semigroups that do not contain any groups except the trivial group. Examples of the latter kind are bands and their commutative subclass, semilattices, which are also ordered algebraic structures. Definition: a semigroup is a set together with a binary operation that satisfies the associative property. For all, the equation holds. More succinctly, a semigroup is an associative magma. Examples of semigroups: empty semigroup. The empty set forms a semigroup with the empty function as the binary operation. Semigroup with one element. There is essentially only one, the singleton, A, with operation A equals A. Semigroup with two elements. There are five which are essentially different. the set of positive integers with addition, the set of integers with minimum or maximum, square non-negative matrices of a given size with matrix multiplication, any ideal of a ring with the multiplication of the ring, the set of all finite strings over a fixed alphabet sigma with concatenation of strings as the semigroup operation, the so-called free semigroup over sigma, with the empty string included. This semigroup becomes the free monoid over sigma, a probability distribution F together with all convolution powers of F, with convolution as the operation. This is called a convolution semigroup. A monoid is a semigroup with an identity element. A group is a monoid in which every element has an inverse element. Transformation semigroups and monoids. The set of continuous functions from a topological space to itself. Basic concepts. Identity and zero. If it has both a left identity and a right identity, a semigroup has at most one identity element, which is then two-sided. A semigroup with identity is called a monoid. A semigroup may have multiple left identities but no right identity, or vice versa. A semigroup without identity may be embedded in a monoid formed by adjoining an element to and defining for all. The notation S1 denotes a monoid obtained from S by adjoining an identity if necessary. Similarly, every magma has at most one absorbing element, which in semigroup theory is called a zero. Analogous to the above construction, for every semigroup S, one can define S0, a semigroup with zero that embeds S. Subsemigroups and ideals. The semigroup operation induces an operation on the collection of its subsets. Given subsets A and B of a semigroup S, the product AB, written commonly as AB, is the set AB, are in A and B in B. In terms of this operations, a subset A is called a subsemigroup if AA is a subset of A, a right ideal if his is a subset of A, and a left ideal if SAR is a subset of A. If A is both a left ideal and a right ideal, then it is called an ideal. If S is a semigroup, then the intersection of any collection of subsemigroups of S is also a subsemigroup of S. So the subsemigroups of S form a complete lattice. An example of semigroup with no minimal ideal is the set of positive integers under addition. The minimal ideal of a commutative semigroup, when it exists, is a group. Green's relations, a set of 5 equivalence relations that characterize the elements in terms of the principal ideals they generate, are important tools for analyzing the ideals of a semigroup and related notions of structure. The subset with the property that its every element commutes with any other element of the semigroup is called the center of the semigroup. The center of a semigroup is actually a subsemigroup. Homomorphisms and congruences. A semigroup homomorphism is a function that preserves semigroup structure. A function f(st) between two semigroups is a homomorphism if the equation f equals ff holds for all elements a, b and s, i.e., the result is the same when performing the semigroup operation after all before applying the map f. A semigroup homomorphism between monoids preserves identity if it is a monoid homomorphism, but there are semigroup homomorphisms which are not monoid homomorphisms, e.g., the canonical embedding of a semigroup without identity in two conditions characterizing monoid homomorphisms are discussed further. Let be a semigroup homomorphism. The image of is also a semigroup. If is a monoid with an identity element, then is the identity element in the image of. If is also a monoid with an identity element and belongs to the image of, then, i.e., is a monoid homomorphism. Particularly, if is surjective, then it is a monoid homomorphism. Two semigroups S and T are said to be isomorphic if there is a bijection f(st) with the property that, for any elements A, B and S, f equals ff. Isomorphic semigroups have the same structure. A semigroup congruence is an equivalence relation that is compatible with the semigroup operation. That is, a subset that is an equivalence relation and implies for every in S, Like any equivalence relation, a semigroup congruence induces congruence classes and the semigroup operation induces a binary operation on the congruence classes. Because as a congruence, the set of all congruence classes of forms a semigroup with, called the quotient semigroup or factor semigroup, in denoted. The mapping is a semigroup homomorphism, called the quotient map. Canonical surjection or projection. If S is a monoid, then quotient semigroup is a monoid with identity. Conversely, the kernel of any semigroup homomorphism is a semigroup congruence. These results are nothing more than a particularization of the first isomorphism theorem in universal algebra. Congruence classes and factor monoids are the objects of study in string rewriting systems. A nuclear congruence on S is one which is the kernel of an endomorphism of S. A semigroup S satisfies the maximal condition on congruences if any family of congruences on S, ordered by inclusion, has a maximal element. By Zorn's lemma, this is equivalent to saying that the ascending chain condition holds. There is no infinite strictly ascending chain of congruences on S. Every ideal I of a semigroup induces a subsemigroup, the Rees factor semigroup via the congruence x rho y. Either x equals y or both x and y are in I. Structure of semigroups. For any subset A of S there is a smallest subsemigroup T of S which contains A, and we say that A generates T. A single element X of S generates the subsemigroup Xn. N is a positive integer. If this is finite, then X is said to be of finite order, otherwise it is of infinite order. A semigroup is said to be periodic if all of its elements are of finite order. A semigroup generated by a single element is said to be monogenic. If a monogenic semigroup is infinite, then it is isomorphic to the semigroup of positive integers with the operation of addition. If it is finite and non-empty, then it must contain at least one idempotent. It follows that every non-empty periodic semigroup has at least one idempotent. A subsemigroup which is also a group is called a subgroup. There is a close relationship between the subgroups of a semigroup and its idempotents. Each subgroup contains exactly one idempotent, namely the identity element of the subgroup. For each idempotent T of the semigroup there is a unique maximal subgroup containing E. Each maximal subgroup arises in this way, so there is a one-to-one correspondence between idempotents and maximal subgroups. Here the term maximal subgroup differs from its standard use in group theory. More can often be said when the order is finite. For example, every non-empty finite semigroup is periodic, and has a minimal ideal and at least one idempotent. The number of finite semigroups of a given size is larger than the number of groups of the same size. For example, of the 16 possible multiplication tables for a set of two elements A, B, 8 form semigroups, whereas only 4 of these are monoids and only 2 form groups. For more on the structure of finite semigroups, see Krohn-Rhodes theory. Special classes of semigroups. A monoid is a semigroup with identity. A subsemigroup is a subset of a semigroup that is closed under the semigroup operation. A band is a semigroup the operation of which is idempotent. A cancellative semigroup is one having the cancellation property. AB equals AC implies B equals C, and similarly for BA equals CA. A semilattice is a semigroup whose operation is idempotent and commutative. 0 simple semigroups. Transformation semigroups. Any finite semigroup S can be represented by transformations of a set Q of at most S plus 1 states. Each element X of S then maps Q into itself X. QQ and sequence XY is defined by Q equals Y for each Q in Q. Sequencing clearly is an associative operation, here equivalent to function composition. This representation is basic for any automaton or finite state machine. The bicyclic semigroup is in fact a monoid, which can be described as the free semigroup on two generators P and Q, under the relation P Q equals 1. CO semigroups. Regular semigroups. Every element X has at least one inverse Y satisfying X, Y, X equals X and Y, X, Y equals Y. The elements X and Y are sometimes called mutually inverse. Inverse semigroups are regular semigroups where every element has exactly one inverse. Alternatively, a regular semigroup is inverse if and only if any two idempotents commute. Affine semigroup. A semigroup that is isomorphic to a finitely generated subsemigroup of ZD. These semigroups have applications to commutative algebra. Structure or theorem for commutative semigroups. There is a structure or theorem for commutative semigroups in terms of semilattices. A semilattice is a partially ordered set where every pair of elements has a greatest lower bound, denoted. The operation makes into a semigroup satisfying the additional idempotence law. Given a homomorphism from an arbitrary semigroup to a semilattice, each inverse image is a semigroup. Moreover, becomes graded by, in the sense that if is onto, the semilattice is isomorphic to the quotient of by the equivalence relation such that IFF. This equivalence relation is a semigroup congruence, as defined above. Whenever we take the quotient of a commutative semigroup by a congruence, we get another commutative semigroup. The structure or theorem says that for any commutative semigroup, there is a finest congruence such that the quotient of by this equivalence relation is a semilattice. Denoting this semilattice by, we get a homomorphism from onto, as mentioned, becomes graded by this semilattice. Furthermore, the components are all Archimedean semigroups. An Archimedean semigroup is one where given any pair of elements, there exists an element and such that the Archimedean property follows immediately from the ordering in the semilattice, since with this ordering we have if and only if for some in group of fractions. The group of fractions or group completion of a semigroup S is the group G equals G generated by the elements of S as generators in all equations X, Y equals Z, which hold true in S's relations. There is an obvious semigroup homomorphism J, SG, which sends each element of S to the corresponding generator. This has a universal property for morphisms from S to a group. Given any group H and any semigroup homomorphism K, SH, there exists a unique group homomorphism F, GH with K equals FJ. We may think of G as the most general group that contains a homomorphic image of S. An important question is to characterize those semigroups for which this map is an embedding. This need not always be the case. For example, take S to be the semigroup of subsets of some set X with set theoretic intersection as the binary operation. Since AA equals A holds for all elements of S, this must be true for all generators of G as well, which is therefore the trivial group. It is clearly necessary for embeddability that S have the cancellation property. When S is commutative, this condition is also sufficient, and the Grothendieck group of the semigroup provides a construction of the group of fractions. The problem for non-commutative semigroups can be traced to the first substantial paper on semigroups. Anatoly Maltsev gave necessary and conditions for embeddability in 1937. Semigroup methods in partial differential equations. Semigroup theory can be used to study some problems in the field of partial differential equations. Roughly speaking, the semigroup approach is to regard a time-dependent partial differential equation as an ordinary differential equation on a function space. For example, consider the following initial boundary value problem for the heat equation on the spatial interval Rn times t0. Let x equals L2R be the LP space of square integrable real-valued functions with domain the interval, and let A be the second derivative operator with domain where H2 is a Hardy space. Then the above initial boundary value problem can be interpreted as an initial value problem for an ordinary differential equation on the space X. On an heuristic level, the solution to this problem ought to be U equals X pu 0. However, for a rigorous treatment, a meaning must be given to the exponential of t as a function of t. Exp is a semigroup of operators from x to itself, taking the initial state u0 at time t equals 0 to the state u equals exp0 at time t. The operator A is said to be the infinitesimal generator of the semigroup. History. The study of semigroups trailed behind that of other algebraic structures with more complex axioms such as groups or rings. A number of sources attribute the first use of the term to J.A. de Séguier in Elements de la théorie des groupes abstraits in 1904. The term is used in English in 1908 in Harold Hinton's Theory of Groups of Finite Order. Anton Sushkwitch obtained the first non-trivial results about semigroups. His 1928 paper Überdiendliche Gruppen ohne das Gesetz der Einjütigenumkehrbarkeit determined the structure of finite simple semigroups and showed that the minimal ideal of a finite semigroup is simple. From that point on, the foundations of semigroup theory were further laid by David Rees, James Alexander Green, Evgeny I. Sergeyevich Lyapin, Alfred H. Clifford and Gordon Preston. The latter two published a two-volume monograph on semigroup theory in 1961 and 1967 respectively. In 1970, a new periodical called Semigroup Forum became one of the few mathematical journals devoted entirely to semigroup theory. In recent years, researchers in the field have become more specialized, with dedicated monographs appearing on important classes of semigroups, like inverse semigroups, as well as monographs focusing on applications in algebraic automative theory, particularly for finite automata, and also in functional analysis. Generalizations. If the associativity axiom of a semigroup is dropped, the result is a magma, which is nothing more than a set M equipped with a binary operation M times MM, generalizing in a different direction. An NARY semigroup is a generalization of a semigroup to a set G with a NARY operation instead of a binary operation. The associative law is generalized as follows. Ternary associativity is SR equals A equals AB, i.e., the string ABCDE with any three adjacent elements bracketed. NARY associativity is a string of length n plus with any n adjacent elements bracketed. A 2ARY semigroup is just a semigroup. Further axioms lead to an NARY group. A third generalization is the semigroupoid, in which the requirement that the binary relation be total is lifted. As categories generalize monoids in the same way, a semigroupoid behaves much like a category but lacks identities. Infinitary generalizations of commutative semigroups have sometimes been considered by various authors.